Okay, we're going to get started now. All right, so welcome back to class. Normal announcements. Your project ideation slides are due tomorrow night. You're supposed to put them in a shared folder. Please label the file name for your slides as your unique name. That will help us make sure you get the credit for those slides that you put in there. If you just name them copy of template, you're going to make the grader sad. All right, so those are there. On Friday, we'll have the team formation event, and we'll give you pizza to encourage you to come. And then we have office hours Monday, and homework 5 has been released. It's also due Monday. Any logistics questions? Yeah?
Just to confirm, that's due at...
I can't hear you, man.
To confirm, is that due at 11:59 Thursday?
What's that?
It's due at... We can done it tomorrow night, right?
Yeah, 11:59, yeah. Yep. Please don't delete anybody else's thing. It's all one big shared folder. All right, any other questions? Okay. So I wanted to finish up on one part of timers, and that's just to talk about the SysTick timer, which is a special timer. So first, we're going to talk about programming paradigms. So generally, every program that you'll write in this class, and you can't think about why you would do something else, is going to be the super loop concept, where there's some part of main, you're going to do some initialization, and then you're going to have a set of tasks, and you're going to sequentially go through those tasks. That's typically how you'd write a program in the bare metal world. And it works pretty well because you guys are generally doing relatively simple things. Your projects can get rather complicated, so it might be challenging sometimes if you have lots of different tasks to get done, but it should probably be able to be done in this paradigm. Now, the challenge here is, say you have a task that's like, I don't know, you have some LiDAR, spinning LiDAR, and you have to measure a bunch of values and do some computation on it. And then maybe you have some button presses here that you have to react to, maybe not button presses, let's just call it a screen update, and then some engine here that has to do some tasks. And what you really want is you want to have nice smooth animation, right? Because you want that user experience to work. And maybe you're trying to track somebody and you're trying to calculate where to hit them with a ball, I don't know, or some target. So the problem here is if these tasks start growing or taking longer periods of time because the computation is harder, or maybe you're waiting for some serial interface to go, then your screen might take longer. It might take longer to get to the screen update. Now you have no guarantee that your screen will be smooth, right? So as your system starts getting more and more inputs, it starts getting laggy. This is the problem with this sort of scenario. And then some way we deal with that is we have some interrupts. So interrupts can help mitigate this to some degree, help you be responsive to the button pushes and make sure that happens. But sometimes you don't really have an interrupt, at least in this paradigm, have we constructed it for updating the screen so you can still have this error condition can occur. So the counter argument is what we call a real-time operating system, which essentially is a fancy scheduler. Now there's lots of ways to implement this. We're not really going to go into it, but I want to set it up so you guys know what a real-time operating system kind of is. That'll set you up for 473. And I'm going to talk to you about why we have the SysTick timer as built into the ARM core, so I'm trying to get you guys ready to think about that. So the real-time operating system paradigm is you have tasks and you assign tasks certain priorities, and then you have some timekeeping mechanism, a scheduler that says, I need to make sure that these tasks are done within this priority or in this period of time. So then you could have something like a screen where you give a screen a higher priority and make sure that it's deterministically done every, say, 30 seconds or something. Yeah.
Is this the same thing as like multi-threading where you have each task on like a different thread, or is that different? Yeah,
you can think about that. Tasks and thread in terms of RTOS are the same thing. Pretty much there's a minor maybe difference, but they're the same idea. And here you're in the world where you have one core, right? You're not going to actually do things in parallel. There are microcontroller class processors like the ESP32, which has a dual core. That's a good time to use an RTOS. Arduinos are probably not good because they're pretty limited. They're like 8 bits or 16 bits. They're not very powerful. And then the STM32 is an okay. I mean, you're running at like 120 megahertz anyways, so like that's a reasonable processor where you could have so many things going on that you might want to have an RTOS. And built in Cube IDE is there's a free RTOS. You just, like literally it's called free RTOS. You can push a button and instantiate one. You'd have to really have a good reason to enjoy that much pain in your projects. So where was I going with this? Just to let you know, you could have a scheduler that would go through and schedule these different tasks for different times, and then you would need a mechanism to do that, right? So that's what we're talking about here. So that's where system timer or systic comes in. And basically it's an interrupt or it's a timer that's built into the core that allows for interrupts on known time schedule. So you could say, okay, do this task here, do this task here, this task here. And what you have to do is make sure your task or subtask is atomic and is guaranteed or should end in this period of time. There's a difference between hard timing constraints and soft timing constraints. Hard timing constraints would say if you don't get it done, your system fails, right? The plane falls out of the sky. Soft timing constraints would be like, okay, you failed to meet that, but the user really didn't notice because they're just touching the in-screen entertainment system. It's not mission critical. But anyways, the goal is to try and get your tasks to end within that period of time, and then you're just going to switch through tasks. You might have tasks that have different priorities, and you want to make sure that those go through. You have a queue, just like you have with your interrupts, and you're making sure that those get done first. Okay, so how does Sysdig Timer integrate it? It's part of the core. It's not one of the peripherals. So in that sense, there's lower latency when you're trying to talk back and forth to it, and it has very fixed function. This doesn't have PWM control because the core doesn't need that. It just has timekeeping control, and there's a dedicated handler for that provided by ARM. I mean, you can rewrite this handler, but it's mapped into the NVIC. So yeah, so here the core, it's all part of the core, and your interrupt vector controller can get inputs from the Sysdig Timer. I'm not going to go through every little piece of detail, but this is just so you know that it exists. It's not a 16-bit timer, it's a 24-bit timer, and basically is a reload value, and it's just going to be counting down. That's all it ever does, and then it decides if something, when the event occurs, when it transitions from one, the counting here transitions from 1 to 0, then an interrupt can go off, causing an event to happen. Basically just shown here is always countdown. You set effectively the auto reload timer or the reload timer. They call it that. They just call it the reload timer, and it clocks down. You have a tick that goes off, and you do a task. There's 4 control registers for this thing, or there's 4 bits. There's a control register for it, but there's 4 bits. 3 of them are control bits, and 1 of them is a status bit. So this tells you what clock source you want to go from. See, tick enable, interrupt enable, and then this just tells you if it's actually hit 0. In case, I don't know, maybe the interrupt didn't go off, you want to check manually, you could use that flag. Yep. You can choose different sources. So you get this comes off the advanced high performance bus, because that's the only bus that really touches the core. Even though we talk about the advanced peripheral bus, we just simplified it for you guys. So the advanced peripheral bus is the only clock that's available, and you get to do a divide by 8, and this basically muxes in, right, to choose that, or you can, and then you have an and that, and it's pretty simple control logic. And then there's 4 system registers. We talked about 1 already. Oh, we talked about most of them. Let's see. So there's the control register. This is the reload value. You have the current time of the tick. And then you have 1 more, which is the calibration register. Again, this just helps you to remember what it is. Let me go through here. No. I want the calibration register. So the calibration register makes an assumption here that you have a certain clock, and it's calibrated to say this is exactly 1 millisecond offset. So if you have a 15 megahertz clock going in there, it will give you the correct value to result in 1 millisecond. And so now you can just go to this register, pull it out, and then put that into your reload register and know that you're going to get a millisecond. Now you can set up the scheduler that's going to go off every millisecond, do some tasks. Again, this is not like, oh my gosh, deep exam question, oh my god, fundamental to timers. This is more like, think what the architects are giving you because they're setting you up to do this task. And this task is to set up a real-time operating system. All right, that's all I want to talk to about this. Is there any questions?
So this is all to make sure that when running a particular task or program that it's within a certain time, things that it moves on to the next task.
This is to ensure that, yeah, okay, you can say it that way. So the goal of this module is to ensure that you have some way to set priorities for tasks and to ensure that you transition from one task to another task without necessarily worrying about did the task complete. So you set up a timing schedule and you say, okay, that task is done. You do a context switch to another task. This is where you will see frames and frame pointers in your code if you're, went through all the disassembly stuff. So yeah, it's just about controlling program execution.
So if the program takes too long, well,
You would halt that?
Priority.
If it takes too long, then you're going to halt execution. So, it depends how you set it up, but if your program takes longer than this to execute, then it will halt execution of that program, do a context switch to another program, which is essentially just, think about like an interrupt. You're going to unstack the thing, put a new one on. Then you're going to go and do this other program, then go through your queue. When you're done with this one, you might say, well, what's the next most important one? It could have been the original one you went to, don't know, but it could be something else. So this ensures that every program gets a slice of the CPU at some point.
So with that, assuming that it doesn't run over time, does it just start the next program and restart the interrupt timer?
Yeah. You get control of how you want to do it. So you could just say, I don't really care, right? I'm hitting all my stuff. I have a light workload. I'll just go idle for a while. Another thing to do oftentimes, depending on your programs, you might, when you're done, you might go into a low power mode to save power. And then you're just going to wait till you wake up, and then you're going to do some other task. And so I've written things for little sensors where you do something like systic, but the interval might be 30 seconds. And you wake up, you do a little bit of task, and you go back to sleep, and then you're waiting for an interrupt from a sensor or something to wake you up to do a task. All right, any other questions? Yeah.
There's sort of treating all the tasks as if they're interrupts and then moving between, or?
It's not treating the task as interrupts necessarily, but it's using, you're not writing them in the handler, but you're saying interrupts control which task is going to go next and when you're done doing the computation for a given task. Okay, so that was just a little bit of review. Now we're going to go on to the regularly scheduled program. We're going to be talking about serial communication buses and protocols, and we're going to start with a little overview of bus architectures. So these are all like the parameters that you should think about when we're going through these other modules. And I've broken them up as 4 different modules. We'll probably get through these 2 today, and then we'll do these 2 next week. So start off here. For those who are excited, there's readings. You can look at the embedded system or the textbook that we have, look at chapter 22. I encourage you all to start being able to read through the data sheet, the reference manual itself. I know the thing is over 1,000 pages. I know what your tendency is. You're like, this thing is horrible. What I'm going to do is I'm just going to do Command F to find the one register I need. And I don't want to know anything about the structure because I want to get the data now. And if I have the data now, I can go on to the next question. I get that. That's great. However, if you understood how the ARM has set up this manual, you could just read this and you wouldn't even need to come to class. It's not that hard to read through this text and understand what it is that the thing's trying to do. In some sense, I'll give you the overview so you have the context, but all the details of like how these things actually work is written in there. And just as soon as you understand the structure of the thing, you'll be able to bounce through them pretty quickly and find all the little information. So my suggestion to you all is learn how to read manuals well if you intend to be doing embedded systems. That is the a learning outcome of this class, is that you can learn how to read manuals on your own, and it's not just searching. All right, so now on to serial communication. So there are lots of types of serial communication buses. You've probably seen them in your electronics. Here is a bunch of parallel buses. And then you have other buses, we call them serial buses, that talk one device to another device. So when you're thinking about these buses, there's a bunch of parameters you should consider, and we'll go through each one of them. And that is whether they're wired in serial or parallel, what's the bits per second? I mean, this should be bytes per second, bits per second. How fast are they? There's usually a trade-off there. There's some timing methodology, right? So like, how do you synchronize between these two things? There's the number of destinations and sources. So you can think about this as topology. Is there just one controller and lots of peripherals? Or is it that there are multiple controllers on the bus? And what's that configuration? We're going to talk about arbitration schemes. So this is about how many and what the structure on the bus is. And this is about how do you determine which one you should be talking to. And in the APB bus, it was literally a flag. It was a select line that went high or low. And there's different methods for different protocols. Then there's actually the protocol layer, which is the format of the data, and is there any redundancy in that data? So we'll go through those. So parallel buses should be somewhat familiar because that was what memory mapped I/O was run on. So you have multiple wires, maybe doing a word at a time. Good for high bandwidth requirements. Say you're talking from a CPU talking to a disk. And I should have said, this is all in the context of two chips talking to each other. On-chip communication still uses this terminology and would use a parallel bus, but will give you a different set of constraints and requirements. So all these lectures are about thinking about how two chips will talk to each other. More expensive in terms of pins and wiring and current requirements. There's just more things going on. So it's not necessarily a lightweight solution to implement, but you got good bandwidth, good speed. And there's a bunch of protocols you've probably heard, PCI, PCI Express, Compact Flash, these sorts of protocols you've probably heard about. And then here's, again, just literal examples. This is a bus structure going from, this would be probably a South Bridge or something, like an Intel CPU or x86 CPU that's going to have a large bandwidth to talk to memory and large bandwidth to talk to the video driver or video controller. So then you need lots of parallelism. This is probably a graphics card. I don't know what this is. Maybe I have no idea what this is. Ethernet, maybe? But here's the PCI slot connector, and you have lots of parallel lines coming in. And this is just an old version, like an old D51 or something connector that has lots of parallel wires. Okay? That's the sort of structure we're talking about. I won't show you this. You've seen parallel buses. I'll show you the serial version in a second. All right, so any questions about parallel in general? Nobody in the back have questions? 0 questions, fantastic. Ready for the exam. All right, so the counter one to that is a serial interface. And here, instead of having a bunch of parallel lines where each line holds a bit of data, we're going to transmit multiple bits of data over time. So this is just showing that there's a time sequence. And so you, in this particular case, say D1 or D0 comes out first, and then D1, D2, so on and so forth. And so now we're trading time for physical number of pins or physical wires. So it takes longer to get out, but we have the advantage of only requiring one line, well, at least for the data in this particular topology. So single wire to transmit information makes things easy to implement. You're going to have some synchronization between the transmitter and receiver. I guess you'd still probably need that in some version for the parallel bus, but so in this case, you'll need an extra wire for the clock. We don't concern too much in the parallel case because there's so many wires anyways, an extra wire for a clock is not that big a deal. Inexpensive for communications and good for typically long distance communication, right? So you're trying to go through Ethernet as an example of a serial interface, even though there's multiple wires, yes. All those wires at any one point are carrying 1 bit at a time, so they're using positive and negative versions of the signal so that they can have better signal to noise ratio. Where you don't really have long distance parallel buses. Can anybody guess why you have short parallel bus distances and long serial distances? Yeah?
Maybe interference between.
Yeah. So so interference is a great one. Any other reasons you might think about?
It's expensive to make multiple chains of long.
Yeah, so you imagine you're trying to have an Ethernet cable go all over this building and it's 32 wires long, right? That's just going to be like literally expensive and painful to use. Okay, so we're going to cost optimize that down to as minimum number of wires as possible. Noise and interference is a big one. If you have multiple wires, now they're going to interfere with each other because you're going to have different data on them, and you have this thing called crosstalk, which is painful, and you have to do lots of signal integrity engineering by actually coating each wire with metal or something, or shielding so they don't talk to each other, which is expensive.
So usually serial is just one bit width.
Typically, yeah. I mean, you might have one transmit and one receive, right? So you have a TX and an RX. We'll talk about that case. Probably going to have some sort of clock arbitration. So you'll have multiple signals, but it's not like 32 data lines. You might only have one data line with other helper signals. Does that make sense? Yeah.
Using like a shift register, like in
Yeah.
4, like when it's just one line.
Yeah, we're going to use a shift register. Fantastic. I'll show that in just a second. So examples are RS-232 Ethernet. USB is the most predominant version of the serial. It's literally universal serial bus. Firewire used to exist. There's IRDA. What does DA stand for? I don't know. But this is a protocol. This is your optical protocol for your remote controls, right? That's considered a serial bus. We'll talk about that later. But it's just one signal, things bleeping, blinking off on and on. You can't really get parallel. Then you'd have to have different wavelengths, the receivers, and then transmitters, and the receiver would have to have multiple wavelength detectors, and it would be painful. So this is just like, and they treat it like your microcontroller will just treat just like a serial interface. It just happens to be converted to terahertz instead of megahertz. And then here's examples like USB. And so here we have data plus and data minus. That is just differential signals. So they have the same line, they just give a positive version and negative version here, so that for each bit, so that the transition is very clear to the receiver because there's lots of noise. There's shielding. The shielding is typically grounded, at least it should be. So there's shielding here, and then there's a metal mesh around that as a ground as well. And then you can go look up your protocol here. So it's positive, negative data, and then power and ground. Let's see. No, I don't want that. All right, so fundamental to, do you guys remember what shift registers are? Did you learn about them in 270? No? Seriously, 270, no shift registers? Oh, okay. Fantastic. Arms were all broken when I asked. Totally fine. Got it. All right, so a reminder of what shift registers are. Let's see. So here we'll enable a clock. How is this going to work? So this is just going to take the parallel data and then sequentially push the data out over the bus to the receiver. And this is the fundamental unit of translating between the massively parallel world, which is your microcontroller, and shifting that and translating to the serial world. So this is like a microcontroller, this would be some peripheral over here, and now you can see these bits translating through. And so this architecture you're going to see over and over again inside your peripherals as a way to send data back and forth. Okay. All right, so things to consider. So there's issues. What do I mean by encoding? I have no idea. Data transfer rates. Certainly, data transfer rates here are faster than this one. I guess data encoding of how it's encoded, whether versus serial versus parallel. You have a lot of pin costs with the parallel version. And then you should have some, in any of these protocols, you should have some error correction or error detection mechanism. Maybe a little less important with the parallel because you're going over short distances in controlled environments, but serial is almost all the protocols have some sort of error correction in them. Data transfer speed. So serial is typically slower. Obviously, you're translating time for speed, so you're going to be slower. But these, speeds are not bad. USB 3 now, or I guess these are USB 2 speeds, are megabytes per second, gigabytes per second. So they're relatively fast. Your internet is relatively fast. It's just that you can get much, much faster speeds. Basically DDR3, DDR4, transmitting data from a processor to memory and back and forth. Now you're in multi-gigabits per second. So that's the fundamental trade-off between the two. Yeah, we talked about most of these issues. So timing, if you both parallel or series could be asynchronous or synchronous, and by asynchronous or synchronous we mean that there's a data line and then there's an explicit clock, and the clock is telling the receiver when to clock in the data, when to latch in this data. So that makes it very explicit. There are protocols where asynchronous, where the receiver has to on its own figure out when to clock data in, right? This has the advantage of you don't need a clock wire, which is nice, but now it's up to the receiver to figure out exactly when, and it may not know, right? It may not even know when the signal's coming in, so there's got to be some arbitration or some method to recover the signal and the clock, so we often call it clock recovery, where you're getting some information, you have to infer or phase lock your clock to that particular receiver.
Like asynchronous, like is it like how does it? Is it like all software that like controls the clock? Like how do you know?
Usually it's a hardware peripheral. We don't want to put programmers in charge of making sure you have time, critical things happening. So they go and they'll make, and we'll talk about some of those methods when you get to some of the later bus protocols, but there's usually hardware methods to help you figure that out. Some protocols, like wireless protocols, will often have a preamble. So they'll have, before the actual data packets come in, they'll have a set of transitions of a known type. So say maybe 8 transitions from high to low or something. And that allows the receiver to lock on to the timing, and then it knows how to recover the rest of the signal. So that's pretty common in wireless systems to have something like that. So timing methods, synchronous. We talked about most of these. Let's see. Yeah. Okay. So device-to-device communication. So you can either have single source, single destination, so point-to-point. This is typically the cheapest because you don't need any arbitration or tri-states in order to select between different things. So this is just a preferred one. UART is often like this methodology. Single to source, so maybe you have a microcontroller that will talk to multiple things, but those things can't talk to each other. So this would be an example of the APB bus controller could talk to multiple the peripherals, but the peripherals couldn't talk to each other. And then you have some that get a little wild and crazy where you have multiple sources, multiple destinations. Sometimes you have multiple controllers on the bus. And then there's got to be some negotiation between the controllers about who's actually going to have the bus at any one time. And here's just a visual example. I don't know why these come out so bad on the screen, but this would be like UART, where you got point-to-point communication. Many structures are like this, where you have a common bus that goes between them, but you could also think about a star configuration where you're the microcontroller and now you're talking to multiple different devices. Oftentimes you have dedicated pins, like 2 UART pins, or 2 sets of UARTs, 2 sets of I2C, and you can think about a star configuration like that. When you get to things like mesh networks, these are often used in wireless systems where you have devices with different capability trying to backhaul data, and then rings and trees and buses and some hybrid stuff are also seen in data networks, so like Ethernet protocols. Arbitration techniques, so this is how do you know, once you have everything linked up, how do you know who should be talking? If you have multiple devices, so say you have here, how do you know that this device or that this controller here is talking to which device? So how did we do that with the APB bus? If you remember, yeah.
Assert the select line for the peripheral we want to talk to and deassert all the other ones.
Yeah, so you said you were going to use the select line to selected the actual peripheral, so that was the way to arbitrate, and then the address bits talk to individual registers inside that peripheral. And then we'll talk, there's a bunch of different ways because it does get complicated. So there's some bus protocols where there are no select lines whatsoever, and now you have to find some other method to decide who's talking and when they should talk. Okay. So this is supposed to be just a quick overview of the concept that you should be looking for as we go through the next lectures. So here are examples of peripherals or protocols we'll talk about. So UART and RS-232, it's a very standard low cost point-to-point solution. I2C, sometimes we call it I2C. Don't even know what it stands for anymore because I've just been working on this so long, but this is a proprietary spec by Philips, and you actually, to use this, to make a device that goes out in the market, you have to register the address of the device and pay Philips a bunch of money so that you can have your device registered. But then Philips makes sure that your address of your little peripheral, say you make a little sensor, doesn't collide with anybody else's address. So it's kind of interesting. They've kind of made their own little market here where they get paid because they instantiated this one. SPI, serial peripheral interface, doesn't actually have a standard associated with it. It's much more free and or open as a standard. And when I say there's no standard associated with it, there's no like IEEE, like here's this governing body that controls SPI. It's more of an agreement between all the manufacturers of here's the common interface modalities, and sometimes you find weird devices that don't implement one of them and they don't have to because it's not beholden to a particular standards body. And these are other ones we're not going to talk about. I think if you know these, you can figure out the fundamentals of these pretty quickly. This one is almost exactly UART, but USB has actually gotten to the point where it's more like RF in a cable than it is just a serial protocol, and it has layers of complexity are more like Ethernet than more like SPI or I2C. So we can just leave these for other classes, and there's enough tutorials online. If you end up using them for a project, you'll be able to find your way through. Oh, and Bluetooth, yes. Okay, so a question for you. Why does ARM use parallel buses for inside the chip, like the APB, and why do we use serial buses for off-device communication, for chip-to-chip communication? So why don't you take 30 seconds or so, talk amongst each other. Yeah.
Parallel bus to talk to FPGA though.
Okay. Why? Yeah, you can do it. Like Intel processor uses a parallel bus to talk to the video card. It should have like an extra higher speed. Penalty if it takes more pins.
Everything shipped to all chips.
I don't think you I think that's the bigger well, yeah, it's slower, and it also
I just don't know if I did it right.
oh, it's shorter to the 6.
All right, what do we think? Why do we typically use parallel, or why does ARM use a parallel bus on chip and use serial communication for off chip?
Because for chip to chip, there's like less distance to go.
Well, wait. So the ARM parallel buses are on chip, so that's like as close as you could be. I don't know if necessarily distance is the most important thing in this case. When I think about distance, that's a fair thing. I'm thinking about like trying to go from chip to chip this far versus a USB cable that far or longer.
There's only so many pins on the chip.
Ooh, why are there so many pins? Why is that a limitation? Explain more.
Maybe another 20 or so or something, so.
Why don't we just put more pins on the chip then? You don't know? That's fine. That's a fair question. I'll show you in just a second. So this is just a reminder. This is the bus architecture for like an 80 or 8008. It's old. This is only 8 bits, but it's very easy to get all the routing here. In fact, how a chip works is typically, you have like your transistor layers, and you have multiple metal layers on top, and then you might have 6 or 7 metal layers. So you can actually have digital logic and then push buses over the top of them without much problem. So the counter argument here is we are limited in the number of pins that you can get. So each one of these little black dots is a pin, and you're limited by the size of your chip. You don't want to make big chips because big chips are expensive. The cost structure is you want the smallest chip. You make a big die about this big, and you cut it up into little pieces. The large, and then your certain amount of profit you make on a die. And so the smaller the chip is, the more profit your company's going to make, and which is inversely proportional to how many pins you can get on it. So you live in this pin-constrained world, and if you come back to this thing, this is literally how these little dots, you're going to take a gold wire, you bond it to this thing, and then wire it to these pins outside. There's only so many you can get on this thing before it just becomes non-economic. There are chip technologies called flip chip technologies where you can put more bumps on top of them, but they are much more expensive and painful to make. Only really worth it for the top-end processors where you really need more I/O.
If you wanted to use like to connect multiple wires to like a limited number of ports, you're really trying to get.
Yeah, so you're saying you have multiple wires in here, and I have one wire coming off, and I could use a mux, right, to multiplex into this? Well, that's what they do, right? So you have things like you have your UART peripheral and which is a communication peripheral. A timer won't work, but UART, ADCs, your camera peripheral, all these sorts of peripherals that live here, and they reuse the pin for multiple functionalities. So you could use it for GPIO, you could use it for an analog function, you could use it for PWM, you could use it for all these things, and that is what your control register, your motor register on your device was doing, right? You were selecting which functionality goes to this pin. So basically you're doing a multiplexer. You still only get one signal out at a time. So you'd have to do time domain multiplexing between those things. And the reality is this pin is only connected to this ever, and so I'm not going to be able to connect other wires to this. So it's almost always going to be one functionality per pin for your device. All right, so does anybody have questions about serial versus parallel in general, or why you would want to have most communication protocols are based, chip to chip is based on serial? Okay. Nope, I don't want that. All right, talk about universal asynchronous transmit receive. Again, those are the readings in the book if you get excited. So the universal, asynchronous receiver transmitter is a general class of types of controllers that kind of switch between parallel and serial forms. Right? They take the massively parallel world of the microcontroller or the processor and shift the data out one by one. And there's a bunch of standards around this. We're going to talk about UART, and then these are the physical interfaces for a UART protocol, which define both the mechanical interface, the connector, and the signaling interface, how high or low, like the voltage levels of the signal and the data rates. So a little history lesson. UART came out in 1971, even before I was born, if you can imagine that there was a time that far along. And back when we thought beige computers looked hot, but pretty much most of these ports have disappeared. However, they called them UART was the protocol, and the standard was RS-232, and that's what these serial ports looked like. And this is called, I think, a sub D9. Sub D meant that this shape, this kind of connector style, and then there was 9 pins in them. Yeah, there you go. And so this was common way to get data in and out. And now it's commonly used I know in the 2000s they started to remove them from computers. That's great, but it's still a very commonly used protocol today. There's billions of devices still being made today based on that protocol. Why? Why are we still using a deprecated protocol? Why don't you take 30 seconds, talk amongst yourself why the industry would make this decision? Why not just kill it finally?
Be able to transition from parallel.
What's the question?
Okay.
Is that the only way to do that though? I don't
Personally, I'm not leaving mine. Is it like
I wasn't paying attention to your backwards. Physical.
Must it be like all fires? So don't
you don't have to switch it.
Like legacy ones cost a lot. Apple ones out, especially USB-C, like a lot of 360 tried it.
All right, what do we think? What could be a reason that the industry has not killed off this device or this protocol, considering it was, it's been deprecated from almost all consumer-grade computing devices?
Legacy, like, compatibility, you don't want to kill things if they're still running on it.
Yep, it's pretty good. So that I would certainly say that there was legacy issues here. So say, starting around here, laptops specifically started getting smaller. And so having this big, bulky connector here just wasn't making sense. And essentially, that's why we went from USB-A to USB-C, right? Because they just need to make things smaller. But that's why they would have kept it around, right? Just a little bit longer, backwards compatibility for these legacy devices. But now we're 25 years past this. Why do we still have devices with USB?
Like maybe more accurate, there's less noise.
So there could be some unique aspects to it from a signal integrity point of view. Okay, maybe. What do you think?
It's still like a really reliable way to go from parallel to serial. There's no better way.
Yes, I think those are kind of related. One more?
Sort of the cheapness, the ease of production compared to like
Yeah, I'm going to take all three of those answers, put them together. Cheapness, it's just so, first of all, it's so fundamental. You're going to see in a second that the way in which you'd have two things communicate is just, there's like not an alternative that's also easy and cheap and reliable. It all fundamentally boils down to something that would look like UART. And so the PC market stopped using it, but the microcontroller market said, oh wait, we have this protocol exists. There's a bunch of people that know how to use it. Well, we're just going to reformat a little bit for microcontrollers. And now that's how a lot of chip-to-chip communication works. Maybe I put these a little bit out of order, but this is what it used to look like. Doesn't really matter anymore. I'll give you a little story. Oh, and there's certain voltage levels, RS-232. If you were finding legacy equipment, then you'd be at 15 volts or 6 volts or 7 volts. This is negative 7 volts to 12 volts. What a weird signaling. This is a low, this is a high. Why? I don't know. I just live here. Okay, so there's different. Now, when I was an undergrad like you, I was working in a research lab, and they said, okay, there's some old legacy piece of equipment and figure out how to get your microcontroller to talk to it. And I didn't know anything about anything, and I kept on struggling for a long time trying to figure out why my microcontroller is putting out positive and highs and lows, and then what was coming out of the RS-232 converter was inverted. I couldn't figure out what was wrong with my protocol. How would that happen? Well, what they're doing is they take signal levels, so like 3.3 volts, maybe 5 volts, and they kick it up to plus or minus 12 volts, and they just invert it. They send it literally through an inverter that just boosts the signal up so that it's loud enough so that by the time it gets over to the receiver, the signals have not degraded too much to noise. So it just took me embarrassingly long time to realize that all that was inside that little piece of converter was an inverter that was had 12 minus 12 and plus 12 rails. All right, so let's get into some of the details. For this particular protocol, there is a dedicated transmit and dedicated receive. So this is will catch everybody. So you have device 1, you're going to transmit out on your microcontroller to say some peripheral device, maybe a radio. And you're going to transmit here, and it's going to go to its receiver, and that transmitter is going to go to its receiver. Now, once a year, I see this from somebody, and I made the same mistake too, where you say, okay, well, this is my microcontroller, and that's a peripheral device, so I'm going to take transmit, it's going to go and connect to transmit. And receive is going to be connected to receive, because this is my transmitter, I'm going to go over here. These things are supposed to be interlocked. But that's not the perspective about how this protocol was made. The perspective was that there was no master or no controller. These devices were of the same, were equal, right? It was originally made so computers could talk to each other. And so now, from this point of view, this is it's the controller, right? Transmit, receive. So my suggestion is, if you're confused at all, on your board, leave yourself extra little pins so that you can manually rewire that if you screw up. Or there's little tricks you can do with 0-ohm resistors, so you can put the resistors this way or that way to connect different things and save yourself the embarrassment that I had of getting it wrong. So here you'll see you got transmit, receive, and ground, but what's missing? There's no clock. So why don't you take 30 seconds, talk amongst yourself, try and come up, how does this device going to know? There's no preamble, I already told you that one. There's no preamble per se. How does this device know when to clock the data in? How does it do clock recovery?
You're saying, how do you know when we finish?
Is it just
How do you know when it's transmitting data?
right? So it's always
Yeah, I get some highs and lows. Well, was it 2 highs or is it 1 high? Was it 2 bits you were sent or 1 bit? Well, I don't know. How would this thing know?
How do you know what you're you can just put it over
use a timer.
Much more fleshed out there.
All right, what do we think? What's some way to figure out when to clock in data on the receiving device?
The other device that is sending data.
They can agree on a transmission rate beforehand, so
Ooh.
you can configure to the same rate, and then synchronize to a clock edge whenever one starts.
Well, I like the first part. You said let's agree on the same, first of all, data format. We got to do that. And then let's agree on the same data rate. So I know the bit width you're supposed to be. But then you said, the last part you got wrong. You said synchronize on a clock. But how are we going to do that synchronization bit after we've agreed about how long a bit is? What are some methods we could come up with?
I guess when the transaction starts by sending like the first bit or something to denote that, you would start the clock on the rising or falling edge of that.
It sounds pretty good. You have to have some feature of the protocol to start timing off of, right? So it could be like a transition from low to high or high to low, where you say, okay, when I see that, then I'm going to do this other thing. I'm going to start my own timer to know when to clock in. So we're going to see how they do it in just a second, but essentially that's exactly correct. So on your Nucleo board, this is your UART peripheral. This happens to be LP, stands for low power UART peripheral. And here there's I don't know what this structure is. Oh, this is supposed to be your bit rate and oversampling generator. We'll talk about how this, our baud rate generator and oversampling method works to get the clock, to know when the clock data in. Then you have shift registers. Then you have FIFOs, and then this can send off UART or interrupts and all sorts of things when data comes in. Okay. And that's essentially just a bunch of shift registers with a clock here to keep track of when to time things in. But the next question is, so this is where you agree on time back and forth, so you literally have to program into your microcontroller, this is my baud rate, or this is my symbol rate of how fast data should be coming in. Then you still need a way to figure out when exactly in time to latch in that data. And so how they do that is, so this is a timing diagram. This is the sender. The receiver in this case is not receiving anything or sending anything. So this is a bidirectional communication or fully duplexed where a transmitter and receiver can be transmitting at exactly the same time. Because you have two separate wires, it doesn't matter. You can just transmit back and forth. But here, what you have is you have a start bit. And this start bit is denoted by the line is always held high. And then a transition from high to low indicates this transition that data is going to be coming. And then right here, you're saying, well, I'm going to keep low for a period of time, and then I'm going to either high or low. These are what these signals mean. So bit 0 can be high or low. And now we just know from this time to this time, you have to have a little timer internal to keep track of then I should be sampling in approximately the center of each one of these things, right? And so this is 8 bits, and then here's a parity bit. The parity bit helps you check to see if the data you got was correct. And then there's a stop bit where you transition up. And you have to be held high for so long so that they know that you're at the end of the transition. Questions? All right. Let me see if I have exactly a slide I'm hoping for. Yes, it's coming. There's different data frames. So in the UART protocol, you can be, the typical one is in 8 bits. You can have 9 bits or 7-bit words. The reason it's usually 8 bits is because that's what ASCII is. So you use ASCII, you're trying to transmit ASCII characters over, and then you get them on the other side, and you have something that's human readable. You can use other types of bits. You get a start bit, a stop bit, a parity bit. You can have up to 2 stop bits if you want to, and you have to agree beforehand how many stop bits you're going to use and if you're going to use a parity bit or not. Yeah.
So, recognizing there was a drop in voltage for a certain period of time.
Yeah.
From a previously held high, they
Correct.
indicate that we're starting some form of frame, which is going to put in data.
Yep.
Kind of this the check and then hold up, and like, okay, now it's ready to use it.
Yep.
So if you have like a device that uses like serial communication, and then I guess you're using a microcontroller, would the device have like within its data sheet like a baud rate, and then you would set your microcontroller to that baud rate?
Yep. That's most problems. That's the first layer of problems when we work with UART. Your computer, you're using Hyperterm or some terminal that the lab gave you. You have UART and you set it to something, and then you thought for sure on your microcontroller you set it to something, and those two baud rates don't mix, aren't the correct, and now you get gibberish. You still might get ASCII characters out. It might look like something because it went through here, and even though it was at the wrong time, it still sampled something. And then you just get like some weird ASCII character you've never seen in your life, and then you're trying to debug that for an hour. That's first layer of UART problems. Parity bits. So parity bit is a way just to check to see if the data that you've sent is accurate. So if there is noise on the line and you had a bit flip, this would tell you that there's a bit flip. It would, or it tells you that one bit got flipped, but it doesn't tell you where. And it's just it's a very crude way. So basically, it's you count the number of ones and the total number of ones. If it's an even, I think you got even parity, and if it's odd, you got odd parity. I think odd is 0 and even is 1. And so the nice thing is that your hardware is going to detect that for you. So your hardware has built-in stuff, and you can get a little interrupt that says, "Oh, my parity is off." Yeah.
So do you want a specific parity? Like, is it you always want like odd or even, or just like
you're gonna count through here and see how many ones you have, and then if you have an even number of those, it's a certain parity.
Different parities just tell you different things.
Yeah, if the parity doesn't equal the number of ones you have, then there was an error.
Oh, I see. So it's basically like putting in a specific value, you're into checking or knowing what value should.
Yep. Oh, what happened there? Okay. We talk about the data rate or how fast that communication is with the term baud rate. Baud rate is not the same as symbol rate. Symbol rate is how many transitions per second. Baud rate is how much information per second. So let's say each frame has one start bit and 8 data bits and 1 stop bit and no parity bits. Think about that case. You might say that, okay, how much data is being transferred through? And you might say, oh, this is my baud rate divided by 8 because I have 8 bits. Well, that's not actually true because you have these other bits here, right? You have these other bits. So your actual, baud rate is the symbol rate, not your data rate. I misspoke before. So this is the actual number of bytes per second you get through. You have some protocol overhead here. That's the definition here is the differentiation. So start and stop bits are overhead. The other thing to think about is this is still not what you're actually going to be able to get through the line. This is just for one data frame, how fast the data frame comes through, but you have to fill that serial line with data. So it might be that your microcontroller spits out a frame and then needs, say, several milliseconds or maybe more like microseconds before the next frame can come out. And then why would that be? Because you're going to go from your core, you're going to have some word, you're going to load it or store it into a memory address, and that's going to go out of your microcontroller. Well, then you have to store another thing in. So you have a series of packets. You have packet, 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 but there's some space in between the packets. So you can't fully utilize that channel and get exactly this rate. That's just like the instantaneous rate for a data frame. All right, so going back to synchronization, so how do you actually do this? We said we're going to use a starting edge to denote when we're supposed to clock in. Oh, there's one piece of information I forgot to say. What could you imagine could be a challenge with this, right? Well, I'll just tell you. If this clock is not perfectly synchronized to this clock, eventually they're going to get out of sync. This one is like, say, 5% faster. Well, eventually, over here, right, they're going to become out of sync. So, this clock error will happen in your baud rate, partly because the source clock you have may not be perfectly divisible into your baud rate. It might be an approximation, or the transmitter might not have a perfect delineation to be fully accurate in the baud rate. So this is only really good for 8 to 10 bits worth of data, and then on the next, every single frame, you're going to calculate when to start looking based on this transition. So because of clock skew between these two domains, you can't rely on this timing all the time. But when do you go and figure this out? So I used to have a nice little animation here that would slide back and forth. It was pretty. I look at this as like the problem is you're pushing a kid on the swing, right? This is saying you're trying to measure when to look here. And the challenge is I don't know when the kid's coming, right? So my daughter, I always pushed her on the swing with my blindfold on, with my eyes closed, right? And so to do that, you have to know I might be pushing air. So you need some way to synchronize with the swinging person. Just like the transmitter sending data on some edges, you need to synchronize with it some way. So you need some strategy of knowing when to push the kid or some strategy of knowing exactly when in time to latch in the data. Again, you know the period of the swing, you know the period of the data because you create on the baud rate, but you don't know when that edge is coming. So you're going to use this start bit to figure that out. And what they do is they essentially have a clock that oversamples. So you have a clock, say it's going 16 times the speed, and you say, okay, I know my baud rate that, say, it's going 16 times, so I know what my baud rate is, so I'm going to set this clock to 16 times. I'm looking for this transition from high to low. Then I'm going to count in 8 cycles. This is where I'm supposed to be. This is the middle of the bit. Then I'm going to go 16 bits because it's 16 times oversampling. And then I'm going to start clocking in here and then there. So this would be 0 and 1, 2, 3, forward. So basically, the penalty here is that you have to have a clock that's much faster and your actual data rate. And that's easy now. Now we have clocks that go 100 megahertz, but back when they started in the 1970s, this was actually somewhat of a challenge and a sacrifice they had to make this clock go much faster than the actual data rate. So does this make sense? How we're going to go and decide when to actually clock in data?
So your UART 16x clock is 16 times your baud rate?
Correct. Yeah. Now you could use different strategies. You could have an 8 times clock. It could be maybe 32 if you really want to be precise. Who knows what right? But it's probably going to be some power of 2 to make life easier. And you have to be able to, when that clock comes in, you're basically going to go 1.5 baud rates to start knowing when to click into the middle of the bit. Yeah, sorry.
What's the value of like going into the middle of the bit instead of like what if you just did like 16 clock cycles?
So I just went here?
Yeah.
Well, now my data is transitioning.
Okay.
All right, so if I clock in here, is it a 1 or a 0?
Gotcha.
And so what you want in almost all the clocking strategies is you want it to be stable for a period of time. So what we're not showing you, and I'll show you in a second, there's a little bit of skew here. So we want it to settle for a while, and we're going to say maybe like a quarter of the time it needs to be settled for a quarter of the bit width, or the period here, whatever this is. Or sorry, from here to here. It needs to be stable for a while so that I know it's clockable. Yeah.
Just to make sure I'm understanding this. You're saying since we have no clock, when you get the start bit comes in,
Yep.
let's say your baud rate is a 16 as an example, you do half of that and then you do the baud rate again, just to oversample, and then to answer his question, just so to avoid that slew rate.
Yep. So this signal is coming from the external world, and this signal is on your device, right? And you don't know exactly, they're not perfectly aligned, the internal device and external world. So if your clock was just the baud rate, well, your square wave could be anywhere in here, and you might not hit exactly right. Or maybe the worst case is you're always hit right here. You're trying to clock in this data, that would be wrong. So by oversampling, you know there's a starting point, and then you know where to start sampling data. And this is all done in hardware. You don't have to do any of this. You just have to know it exists, right? Your UART peripheral does this task for you. And so your job would be, you should be able to, after going through lab and working on serial interfaces for a while, is be able to understand UART protocol. So here we have, say this is a transmit pin, it's transmitting to the cellular device. It starts up high, we see a low sequence, right? There's a start bit, it's been held low for a period of time. You would have to already know what your your baud rate is, and you could calculate, okay, using time scale here, when half of it was over, and then or half of it here, and then a full 16 over sampling here, and then you go and calculate right here each one of those things to recover the bits. Now, we didn't talk about this before. There's no set protocol whether UART is most significant bit first or least significant bit first. You just have to agree with the transmitter receiver, have to agree on that beforehand, just like they have to agree on the baud rate and the number of stop bits and if there's a parity bit or not. What questions do you have? Yeah.
What's the reason? So, since you have to add a secondary clock inside the processor and stuff.
Yep.
Is the reason you don't send the clock signal through because of degradation of the clock signal?
You don't want to use the pins. That's it. We're all this pain and overhead is just basically because you're limited on I/O pins.
Okay.
Why did they originally do this? Like in the 70s, it was probably a clock skew issue. It was probably too painful to send all that data around.
But you have an issue with if you lose a clock voltage signal versus one piece of data, would that mess it all up?
Yeah, sorry, you're saying if, say, the voltage on your clock went too low?
Yeah, if it was metastability.
Yeah, that would totally screw everything up. So maybe you could think about this being more redundant because now you're not relying on a clock signal, but then the other side is clock signal tells you exactly when to clock in. So I don't know what design problems they were facing back then. Yeah.
You're technically still relying on a clock signal. That's just internal. It's
Correct.
not coming in from the outside.
Right, but the problem is you have to synchronize there, right? And now this is always a perennial problem. You're trying to synchronize between clock domains. If you're off by a little, bad things happen. So you need a resynchronizer, which is essentially the structure we just showed you by oversampling. All right, so just thinking, kind of connecting this back with the rest of your STM. Right, so here you have data coming in. It's going to go into a shift register. You have a data register, so this is going to take it from serial, put it into parallel. When this register is full, it's going to throw an ISR, and that ISR goes off. Then you can do some tasks. In fact, you can get an ISR when it's transmitted. So you go and put a piece of data in here. You say go, it goes off, and then it'll throw an ISR to tell you to do the next one. Right. So now you have essentially a method for the ISRs to do flow control and send multiple characters at a time. And so again, the programming paradigm is you do a bunch of setup. You go through, and you set up these registers to be on and connected to the GPIO pins and sending data at particular baud rates and all those things. And then you're either pushing data into and calling an ISR, so you're saying, okay, I want you to push this data out for me, or you're waiting for data to come in, you pop in the ISR, read this buffer, put it into storage, and then get out of your ISR. And then in main, you can do some function on top of the data that you put in memory. And going back to this is kind of a typical interrupt scene where you have a hardware, you're trying to set a string of data. You can go and set up your interrupt such that when it sends the first byte, then it hits the interrupt again, you send a second byte, third byte, and that way you can get a string of data sending off relatively quickly. And there's no reason why you couldn't do it in a while one loop where you go through, you send out a piece of data, go all the way back through a loop, send another piece of data, another piece of data. Interrupts is just a formalized way to ensure that you get it out as fast as you can. So the kind of modern way modern usage of UART is typically one microcontroller talking to one other chip. It used to have the UART protocol allowed multiple devices to talk to multiple devices. We don't do that anymore. But say you want a microcontroller to talk to a computer. Well, your STM32 happens to have a USB controller on it. Let's assume it doesn't. Not all microcontrollers do. But almost all microcontrollers have a UART interface because it's so simple. So what you do is you buy an extra chip. I don't actually forget what this company is. It's FTDI, and they make UART to serial interface chips, and everybody uses them. They've just become ubiquitous. I'm sure there's other companies that do it too. But now what happens is you're going to talk to UART to this thing, and then it has a whole USB interface into it, and it takes the UART signal and sends it to your computer. It takes care of all the negotiation, because USB isn't just a serial communication like we've talked about. It has layers on top of it where there's acknowledgments and shakes and talk back and forth and all these agreements, and it's just too much overhead oftentimes for what you want to do with a little microcontroller. So there's this market for this chip. From your microcontroller's point of view, it's just a serial interface. It talks to your computer, and your computer will have like a hyper terminal or some Python program which is just pulling data in and out. And so these chips often make it very nice to use. And then the next version of these is they have what you'll use probably in your projects is they have Zigbee or XBee chips, which is basically UART to wireless, to 2.4 gigahertz or to Bluetooth. And again, you don't want to know how Bluetooth works. It's horrible. But you're just going to go and send in UART chips, and it's going to be like a modem that sends over to the other side. And so all the wireless part is taken away from you. You don't have to know how it works. It's just data pops into your Python script or your terminal on your computer and send data back and forth. And for your projects, that's really nice, because sometimes you want to debug. Like, why is my little robot always doing crazy things? Or like it's autonomous, it's trying to move around, and you don't want to have cables and running after it with your laptop. We can just have it send diagnostic messages over Bluetooth saying, oh, I got a left command, I got a right command, this timer went off. Now you at least can figure out what the weird state of your device is. So that's a really useful tool for debugging, but just getting data on and off a device. Any questions? Okay. Yeah, I basically talked about Bluetooth, talked about these chips. Let's see. On your particular microcontroller, there's actually 3 UARTs. 3 URS. I forgot what the S stands for. Universal synchronous. I think this universal synchronous. No, it can't be synchronous. None of my notes don't know what it is. I'll have to remember, but there's up to 5 UARTs. There's one low power UART. The low power UART has a nice capability of it can actually wake up the microcontroller when there's traffic. So you can be in ultra low power mode and it doesn't really consume that much power. These all have FIFOs, 8 bits. So you get to have one register full of data before, and then you have to service that from your interrupts before the next byte comes in. And then each one of these UART modules has a dedicated interrupt on it. So there's lots of different functionality. If you wanted to have 3 radios on your device for some reason, you could do it. All right, so pros and cons. Only uses 2 wires. That's great. No clock for signals. It really reduces the wiring burden. You always have to have ground. That's one that people often forget. they'll put UART, and you don't need the GPIO pins. These are for other reasons. These are for like flow control for the Bluetooth specifically, but UART here, remember you have the crossing structure, and they'll hook them up and they'll say no data is going through. Well, if you have a USB powered thing and a battery powered thing over here, and you haven't connected them to ground, or the two ground pins together, well then no current flows between them, right? So you have to, current always flows in a loop by definition, and so right now you have no return path, so no current wants to go into this thing. You might get some random data, a little bit of signal, but it won't be robust. So when you're doing your labs, make sure you actually connect not only TX to RX and RX to TX, but also the ground wires. So at least there are 3 wires that are going to be required. So cons, the size of the data frame is limited to about, really it's 8 bits, but you could get 9 bits out of it. It doesn't really support multiple peripherals or multi-controllers. There was a way to do that. We're not going to implement that anymore. It's not implemented on your devices. So it's one device to another device. Your hardware oversamples, maybe it's a con, but realistically it's taken away for you. You don't care, right? But that is maybe a con, a conceptual con. And then devices have to agree a priori. Right, you can't just, it's going to be hard to hot swap things. That's not what this protocol is good for, where you connect 2 things together, they just start working. Maybe some other person has connected some peripheral in as part of some consumer electronic devices. That's not going to work. You have to reset everything. You have to agree on everything beforehand. And then your internal clocks have to be accurate and stable. There's calculations you can do to see what your clock rate is and what your desired baud rate is and what the error is. And if the error is too high, you will actually get errors in the last couple bits of your, or statistically you'll get more errors in the last bits of your transmission. So just a heads up, just because your microcontroller says you can try to do that baud doesn't mean it's perfectly that number. It might be a little bit off. All right, that's all I want to talk to about UART. We'll save I2C and SPI for tomorrow. Is there any last questions? Yeah? The question is, can I explain why there's 9 bits or 10 bits or 8 bits in the data frame? Why is a question. I can tell you that it is this way. This is just historically how the protocol has been set up. So I would say the most common is to have 8 bits, one start bit, 8 bits, a stop bit, and a parity bit. That's pretty common. But most microcontrollers will support 9 bits or 7 bits as well. Any other questions? All right, you guys can go. I'll see you all on Friday.